Okay, let's define a plane. We go in this menu here, define a new plane, give it a name, we give it a description, and we can start by defining the main wing, the most important part of the plane. The way this is done is by defining wing sections, highlighted in red here, at different positions of the wings, span-wise positions. Initially, we have two positions, one at the root, one at the tip, 1 meter away, with chords predefined but which we will change, and no foils. So let's leave the span as it is right now, and the chords also, and maybe we want some dihedral at the root, so let's exaggerate this, 5 degrees, and you can see the dihedral here appearing. And we'll use the AG25 modified foil for this plane, for this wing. And we have a nice 3D wing that shows up once we have defined the foils. Okay, 5 degrees is too much, so let's go down to 1 degree. And I'll want some washout or twist at the tip. So let's put 1.5 degrees washout. Negative always. And it's a bit too straight, so I'll insert a section in between at roughly 400 millimeters with a chord of 170 millimeters and an offset of 10 millimeters to get a nice straight trailing edge. And I want it to be a 60-inch wing, so let's change the span of the outer section. There, that's a smaller section here. Okay, still a bit too much, so 370. There we are. Yeah, it looks nice, and a bit more dihedral on the outside panel, so let's say 2.5 here. And we have a nice wing. Paneling. This is important for the analysis. You should try to increase the panel density where the geometry changes. Here we don't have enough panels on the outer panel. This is due to the sine distribution, so we'll change to cosine, and you can see that the panels look nicer, and we'll also increase their density to 17, let's say, or 13, just so that the analysis is not too long. And we'll increase the density in the middle, also 13 panels here, so we can see the panel density changing. Right, don't like this color, so I'll change it too, but that's really a personal thing, not good either. Oops, sky blue, there we are. Okay, and I'll say this. Next we define in the very same way the elevator, and my favorite foil for the elevator is the NACA 009. Doesn't really matter, but I've always liked this one. It's a bit too dark. Let's make it this color. Okay, panels, looks good. We could densify, increase the density maybe, but so that the analysis doesn't take too long, I'll leave it as it is. And same for the fin. We use again the NACA 009, 0009. Right, and check the panels. Yes, look good for a first analysis. Okay, so we have, let's check the dimensions of our plane. We have a tail volume of 0.47, which is quite good. We'll check the wing load a bit later. One thing which is important at this stage, and that's really a calculation, a numerical thing, we need to avoid that two wings are in the same horizontal plane, and this is the case here. The two wings, the main wing and the elevator, are in the same plane defined by z equals 0. So what I'll do is I'll offset slightly the elevator and the fin, This is just to avoid that it's to avoid divisions by zero when the analysis is run. And it won't make any difference or otherwise on the results. To have a stable plane, we need to put some pitch down angle on the elevator. That will improve greatly the overall stability. And last, I won't define a body. I don't recommend using a body, and I recommend that you check the guidelines to understand why. It does not improve significantly the results, and it creates some issues. On the other hand, it makes a nicer aircraft to visualize. Okay, and here's our plane. Looks good. So just to make sure we save. And at this stage, it's not necessary, but it's not compulsory, but I recommend that you define your plane's inertia. It will save time later on. So once again, current plane, define inertia. The main wing, I'll use 300 grams, 300 kilos, so that's 300 grams. And we'll add some point masses, 0.025 kilos for the right servo, which will actuate the right flap, the right flap. We need to position it correctly with roughly 15 millimeter offset in the X direction, 500 in the Y direction, and maybe 15 in the upwards direction. And same, we need to define the left servo. Same way, because we want a symmetrical wing, otherwise we'll have issues. 50, but then minus 500 and 15 here. Okay, so the total weight of our wing is 0.350 kilos. Okay. And I rather work in grams than kilos, so I'm changing the units, options, units, and switching to grams here. Okay. Let's see if our masses are correctly positioned. Okay. Well, the servos are perhaps a bit too forward, so let's modify that and move them backwards. 80. Okay. So what the program does, it uses this value as a overall density for the wing and uses this value as point masses, and this will be used to calculate the inertia of the wing later on. Okay, looks better. I'll save the project just to make sure once again, and do the same thing for the elevator and the fin. So the elevator, its mass will be 30 grams. The fin, let's say 20 grams. And I'll add some extra masses to account for the body. So we'll add some nose lead, let's say 150 grams. 200 meters in the nose, 200 millimeters in the nose. This is going to be the nose lead. Then battery and receiver here, roughly 80 grams. Forward 100 millimeters. Okay, and then the tail servos, 25 grams each, which will be 50 grams, and roughly, let's say at the origin, that looks good. Okay, we'll need to add some mass to account for the fuselage, so perhaps 100 grams or 80 grams forward part of the fuselage. And this will be minus 150 millimeters. The middle part, again, let's say 80 grams, 100 millimeters part, and rear part maybe a little less, 50, and this was going to be 450 millimeters backwards. Okay, and this positions our COG 186 millimeters from this point here, which is a bit too much. So what did we do wrong? Let's see. Okay. Oh yeah, I put 300 grams for the elevator. That's the issue. I'll modify that. Okay, this is going to be much better. And now we're 47 offset, 47 millimeters behind the leading edge, this point here, of the leading edge of the central chord of the plane. So that looks a bit forward, but we can start the analysis with this value. And I'll save this plane here.